Okay, so these notes are for section 1.5. It's the application, real world problems dealing with quadratic equations. So all of these examples will result in some sort of equation that is a quadratic. And then we will use the methods that we used in the last section to solve them, right? So we'll solve the resulting quadratic equation using the factoring method, the completing the square method, some other methods that we used in section 1.4. Okay, so let's look at this first example. All right, so a piece of machinery cuts sheets of thin metal, so like sheet metal, for example, such that the length is twice the width. So when we get this sheet of sheet metal, the length is going to be twice as much as the width, and so we've already sort of set that up, x being the width, 2x is the length. Now we know that's always the case. Okay, that's a given. All right, equal size squares, 10 centimeters by 10 centimeters, are cut out of each of the corners of the sheet metal. So for example, this piece is going to get cut out, this piece is going to get cut out, this piece will get cut out, and this piece, this corner, the square, will get cut out. And then this thing will get folded up on these little dashed lines here, will get folded up to create this open box. All right, so an open box, open top metal box is then created by folding up the resulting flaps. If the resulting volume of the metal box is 7,500 centimeters cubed, then what is the dimensions of the original sheet? Now I know the original sheet has a length that's twice the width, we know that, but like what is it? Like what is this length? What is that length? Okay. And so what we have to do is think about, okay, what's the volume? The volume of a rectangular prism is just the three dimensions, right? I mean, so if you want to call it width, length, height, whatever you want to call it. So I'm just going to call it base times the height times, I don't know, maybe the length, right? The length of it, or you want to call that the depth, how far back it goes, whatever you want to call. So a base times the height times the length. Let's call this would be the base. Let's call this the height, and we'll call this the length or the depth. But again, it doesn't matter what you call it, there's the three dimensions. Okay, so let's think about where these things are up in our picture and relate them to x. So like we have to write an expression with just one variable. We've already let the width of the original sheet metal that we start with, we've called that x. So how does that relate to b? So b would be this thing right here, right? So that length is b. And so how is that relating to x? So hopefully you see that b is just what's left over from the x after we cut these two squares out. Remember, 10 centimeters, 10 centimeters, 10 centimeters. So the b is going to be x minus the 20 that was taken out in those two dimensions. So that's going to be our b, that length here. Okay, and then the height of the resulting box, the height, that would be this thing right here, right? Or if we want to think of it as this thing right here, those two edges, when they get folded up, are going to be touching each other. And so that's just 10. And then find the expression for the length. All right, the length of the box is going to be sort of this dimension here. And how does that relate to x? All right, so that's going to be 2x minus the 20. So it's the length of the original sheet minus this 10 and this 10 here. Okay? All right, and then let's go ahead and put the volume in 7,500. And so now we can see that this is going to be a quadratic equation. We have an x times an x, right? An x term times an x term. So it's going to be x squared. Let's simplify that. Let's simplify it and set it equal to 0. And then we'll evaluate the equation and figure out, okay, what do we want to do with that equation? Okay, so let's leave this 7,500. Actually, let's go ahead and divide both sides by 10. That'll make it easier. So that's 750 equals, and then let's FOIL these together. So ignore the 10, FOIL these together. That's going to be what? 2x squared, and then minus 20x, and then minus 40x, and then plus what? 400. Okay, and let's again bring all that, simplify these like terms, and then bring the 750 over. So that gives us 2x squared minus what? 60x. And then when we bring the 750 over, we subtract that, so that'll be negative 350, and that should be equal to 0. All right, so we want to solve this thing. First thing we probably want to do is notice that they're all divisible by 2, all of the terms, and so let's divide everything by 2. Remember, it's an equation, so we can do that. If it was just an expression, we would factor a 2 out and leave it kind of out in front as a monomial. But here, what we're going to do is divide everything by 2. X squared minus 30x minus 175 equals 0. And now, it might be hard to look at this and know whether it's factorable, but it's pretty quick since the leading coefficient is 1. Let's see if it's factorable. If it is, it's always quicker to solve this using factoring rather than trying to plug all these things into your calculator. So let's see, we have x and x. See if you can factor that. Pause the video and see if you can factor it, and then I'll show you whether it is or not. So yeah, 175, two of its factors are 35 and 5, and the difference of the outer and the inner would be 30. So this one's got to be negative, this one's got to be positive. And so now when we set each of those binomials equal to 0, we get x equals negative 5, and we get x equals 35. Now often, we have a quadratic equation, so we're going to have two solutions, makes sense, but in the context of the problem, often one of those two solutions won't work. Sometimes neither one will work. Maybe there's no solution. Maybe there is no box dimensions that would give us a certain volume. So in this case, we would have to just eliminate x equals negative 5. Clearly, x cannot be negative. Indeed, we know just because we're cutting 10 off of it, we know x has got to be greater than 20, right? There's no way it can be less than that. So if I got an answer, even if this wasn't negative, if the answer was less than 20, I would have to ignore that one too because of the restrictions in the context. All right, so we have x equals 35 centimeters, but let's make sure we've answered the question, right? So it says what is the, I guess what are, not what is, but what is the dimensions of the original box? All right, so we know the width is 35, so we have 35 centimeters by, and then twice that, so we have 70 centimeters. Okay, so again, make sure that you're answering the question that they ask. Don't just find x, because x may not be the answer that they're looking for. Okay, all right, let's go on to the next problem. This one we're using the Pythagorean theorem. And remember, the Pythagorean theorem is a squared plus b squared equals c squared, where a and b are the two legs. A doesn't necessarily have to be the smaller one. B could be the smaller one, doesn't matter. But a and b are the two legs of the right triangle. C is the hypotenuse. So if we look, at this triangle over here, clearly that's going to be the right angle. This will be A, this will be B, and let's call this one C then, the hypotenuse. A and B doesn't matter, but this has to be C. It's opposite the right angle. All right, so let's read the question. A property lot is in the shape of a right triangle. The longer leg is 10 meters shorter than twice the length of the short leg. The hypotenuse is 10 meters longer than the longer leg. Find the length of the three sides of the lot. Okay, so go ahead and come up with expressions for these sides. Yeah, A, B, and C, but we want expressions So see if you can come up, pause the video, see if you can come up with expressions for these three sides that we can plug in. They all have to have the same variable. Like up here we had all the variables were x. We have to have all the same variable. So go stop the video, try to do that on your own. Okay, so what I'm going to do is I'm going to do everything in terms of the short leg. So I'm going to refer to this as the short leg, A. And now I know that the longer leg is 10 meters shorter than twice the length of the short leg. So take the short leg and twice it, that's 2A. And then the longer leg is 10 meters shorter than that, right? Shorter than twice the longer leg, all right? And then the hypotenuse is 20 meters longer than the longer leg. So we have 2A minus 10, that's the longer leg, and it's 20 more than that. Now I'll simplify that in the next, kind of when I write it all out. All right, so we know we have A squared plus B squared equals C squared. All right, and so now we just plug the expressions for the three lengths into this. So A squared, that's not going to change, plus we have 2A minus 10 quantity squared, and that's equal to, and let's simplify this. Let's not put it in like this. Let's call it 2A plus 10 quantity squared. So we'll combine these like terms, okay? And now, again, we're going to have a quadratic equation. We just need to simplify and set it equal to 0. So let's expand these. So we have A squared plus, this will be 4A squared. The center term is twice the product of the two, so that'll be negative 40A, and then the last term squared, so plus 100. On the other side, similar thing, we have 4A squared, twice the product of the two, so that's plus 40A, and then plus 100 again. All right, now this one's pretty simple to simplify. We have the same thing on both sides here, so I know those are going to cancel. Hundredths are also going to cancel. I'm going to bring this 40A over. I get A squared minus 80A equals 0. All right, and then we want to use factoring, but this one's a real simple factoring because, you know, generally we have ax squared, x squared plus bx plus c equals 0. In this case, the constant is missing, right? The constant is 0. So this is really simple. When we have an equation like this, we simply take out the variable. So here we can factor a GCF of a. We don't divide by a, we take it out. We do a times a minus 80 equals 0. Okay. If we divide it through by a, it decreases the degree from 2 to 1, and it only gives us one solution. Now, in this case, you would have been okay because, I mean, obviously, the two solutions we get are what? A equals 0 from this one, right? We set that equal to 0, and we set this one equal to 0. So A equals 0, A equals 80. So if you had divided by A, you would have still gotten the one right answer. Clearly, based on our context, A can't be 0, right? I mean, the length here is 0. Then this would be negative. It wouldn't work, right? It can't be possible that the side is 0. So you would have kind of been okay if you'd done that. But generally, you don't want to divide through by A. Before up above, we divide it through by 2. That's a number. We can divide through by 2. We don't want to divide through by a variable A. That causes problems because that now would give us only one solution rather than the two that are possible because this is a degree 2 or a quadratic equation. All right, so be careful. Don't ever divide through by the variable. In this case, we still want to eliminate it, but you don't want to eliminate it. Don't want to divide through by that variable. Only divide through by numbers that are GCFs that are numbers, not GCFs that are variables. Okay. And so now, did we answer the question? Right? We want to. Okay, so we know what A is. So the short leg. So let's do this. The small leg is 80 meters. All right. What's the longer leg? So we just plug that in. That's 160 minus 10. So the long leg, that's 150 meters. And then the hypotenuse, that we plug it into this, or maybe plug it into this one, that would be 160 plus 10, so 170 meters. All right, so again, don't just find the one side and then say, oh, that's my answer. Make sure that you're answering the question, the lengths of all three sides we want, so you want to list them all. All right, let's go on to the back page of our notes. Again, we're continuing with applications. All right, so now we're going to talk about what we refer to as projectile motion. And so that would be throwing a ball up in the air, or shooting a cannonball out of a cannon, that kind of a thing. So just know that when we do these types of problems, we neglect air resistance. So that way, if I throw the ball up in the air, we pretend it's like almost in a volume. So often, depending on the shape, depending on the weight of the object being tossed in the air, neglecting air resistance isn't a big deal. Things flying very fast have a lot more air resistance. So if I'm just tossing a ball up in the air, it's not going to be too bad of an estimate. But the formulas get way more complicated, and you need all kinds of calculus, so we're keeping it simple. Neglect air resistance. All right, we're going to think of it as a function. So this does not mean s times t. This is a function s. We use s because it's like, in physics, we use s to denote like location, right? Sometimes we might use h of t for the height. So we're thinking about, if we throw this up into the air, we might think of h of t. Again, that's not h times t. It's the function h, which is the height, and the variable is related to time. So the location of the object thrown into air is a function of time. So it's s of t is how we say that. All right. So then the height, s of t, in feet, so it's measured in feet, of an object projected directly upwards from initial height of s sub 0. So that's an s with a subscript 0. We call that s naught sometimes, not meaning the English word, like an old English word for 0 is not. And so we'll say s naught, or initial location, initial height in this case, in feet. And then v sub 0 is the initial velocity. So if I'm throwing it up, the ball is throwing it up in the air, it leaves my hand with a certain initial velocity that I've imparted upon it as it leaves my hand. So that is v sub 0. All right, so the function is the function. It's the height with relationship to time. It doesn't really say, but it's in seconds. Time is in seconds. I'm not seeing it in here. Velocity, feet per second. All right, time is in seconds as well. Oh, here it is. T is in seconds. All right, since the object left my hand or left the cannon or whatever. Gravity is the only thing pulling on it at that point. Okay, so negative 16. That negative 16 relates to the gravitational pull. Has to do with the force of gravity. The 32 feet per second squared is the the force due to gravity, or acceleration due to gravity. And so t, that's just time squared, initial velocity times t, plus then the initial height when it leaves my hand. Okay, now This is, of course, assuming that we're dealing with feet. If we are dealing with meters, then this coefficient changes. And so if you remember, acceleration due to gravity is 9.8. I think it's something like 9.8 meters per second squared. And so it's just a coincidence. It has to do with the physics and the mathematics behind it, but this is half of that. Just like up here, the acceleration due to gravity when you're dealing with feet is, well, I guess it's negative actually because it's going down, but 32 feet per second squared. Again, that's acceleration due to gravity, and it just happens the fact of mathematics and the physics. That's why we get 16. It happens to be half of that is all. Okay. And again, if you're on a different planet or if you're on the moon, that number in front will change, but the equation will be the same. Okay. All right, so let's look at the example. A projectile is launched upward from the ground with an initial velocity of 73.5 meters per second. So that is v sub 0, right? V sub 0, the initial velocity. And it's from the ground, so that means the initial height, s sub 0, would be equal to 0, right? So it's from the ground, not 20 feet in the air, but it's leaving the ground, okay? And so when we talk about these projectiles, it's not like, I don't know, it's not like a missile that has an engine or it's being thrusted out the back. It's not that. This is just a cannonball. It has no internal movement. It's just gravity and the initial force that you project on the thing, and nothing else is working on it. All right. So after how many seconds will the projectile be 100 feet above the ground? All right. So that's the height. So that's what we're going to put here. S of t is a function of the height, and so that is the height. So we're going to do 100. That's the height at a certain time. We just don't know what that time is, but we know what the height at that certain time. So at t equals what? We don't know. That's what we're looking for. What's happening? Well, the projectile, it time 0, it leaves the ground, goes up in the air. At some point, it's 100 feet. It's 100 feet in the air. We want to know what time that happens, right? What time is it at 100 feet above the ground? Okay, so we write in negative 16t squared. The initial velocity, we put that in, 73.5 times our t. If we want to put that in t squared in parentheses, we can, I guess. Don't really need either one of those. And then plus the initial height, and the initial height was given to us. It was at the ground, so that would be 0. All right, so again, this is a quadratic. We just need to solve this quadratic equation. So we want to bring everything to the same side. Oh, you know what? This is meters, so I'm using the wrong equation. So it's not 16, that would be feet. This is negative 4.9. Okay? All right, so what I want to do is probably just bring all this to the same side. Also, it's always helpful to have your leading coefficient be positive. So rather than bring this 100 to the right, let's take these two to the left. So we have 4.9 t squared minus 73.5 and then plus 100 equals 0. Okay. These have decimals, so maybe it'd be nice if we multiplied through by 10. Sometimes that's helpful. I don't know. Let's try it. 49t squared minus 735 plus 1,000 equals 0. I don't think all these things are divisible by 49. If they were, it'd be nice. We could divide through by 49, but I don't think that's going to help. certainly 1,000 is not divisible by 49. So, and this is not factorable. In this case, we're going to get a decimal approximation as an answer. So let's go ahead and just use the quadratic formula. All right, so we have t instead of x. We have t this time. The variable that we're using is t. So t equals, I'm sorry, I lost my t in my equation here. Sorry. There, t. So there's my b. So I have negative b, so that's 735. Plus or minus the square root of 735 squared minus 4 times 49 times 1,000. All right, and that's all over 2 times a, or 98. Okay? So if you just take, at this point, just pick up your calculator and plug all this in. This becomes 735 plus or minus the square root of 344,225 divided by 98. And then simplifying this, that's 735 plus or minus, end up with, I'm just going to go to the nearest tenth, so 586.7 over 98. Now, we don't want to leave this as an answer. This would have been an irrational answer, but here we're looking for like a time, right? So what's happening here? So the projectile leaves the Earth at ground zero, goes up in the air, and then comes back down. Now it's really going straight up and straight down, but just for the sake of not being able to see it, if I go straight up and straight down, I'm kind of drawing it a little bit sideways at the same time. So at some point, it crosses through the 100, and again, this is probably not even close to being to scale, but 100 meters at some point. So it makes sense that there should be two answers. It'll pass through the 100 point going up, and then it'll, assuming actually that it goes up, right? So you would get no solution here if, let's say this thing went up at 90 feet and came back down, 90 meters and came back down, then you'd get no solution. So the fact that this radicand is positive means that we have two solutions. Okay, and so if we did it to let's just do it to the nearest tenth of a second, I end up with two solutions here. I get 1.5 seconds, and then 13.5 seconds to the nearest tenth. It's not exactly those, but it's the nearest tenth of a second. Okay, and so of course I haven't really drawn this to scale. It goes up pretty quick, stays up, goes up higher, and then comes back down. So not drawn to scale, but that kind of gives you the idea. Okay, so about this much. These are a decimal approximation. So if you want to say about 1 second and 13.5 seconds. All right. Part B says, how long would it take for the projectile to reach the ground? So for example, start here, you go up, and then how much time would it take for it to come back and hit the Earth? Okay. So if we think about it, what will that height be, right? We don't know the time. Again, we don't know what the time is, but we know the height, and we know the height should be 0 because we want it to come back down and hit the ground. So the height would be 0, and so negative 4.9 t squared plus 73.5 t, and then plus the 0 if we wanted to put it in there. Following the initial height is 0. All right, so we don't really need that. It's already set equal to 0, so now we can just solve this thing. In this case, this is that case where there's no constant. So let's do this. Let's factor out. Well, we can multiply through by a negative, and get rid of this negative and make this negative instead. So if we want, we could say 0 equals 4.9t squared minus 73.5t. And now let's factor a t out. So we get, so t times 4.9t minus 73.5. And that's still equal to 0. And so, we have two solutions. We have t equals 0. That's, back here when this thing started. At time 0, it was on the ground, right? The moment we start this whole thing, it's on ground level, traveling upward at an initial velocity, right? So that's one solution, but that's not what we're looking for. That was the start of this whole thing. We want to simply divide this out, and we get t equals, let's see, we set this equal to 0, 73.5, and divide that by 4.9, and that's exactly 15. So at 15 seconds, so it goes up, 15 seconds later, it's on the ground again. Okay, so 15 seconds is when that thing hits the ground. Okay? All right. The next one is just some modeling. So they give us an equation. So based on figures from the period of 2000 to 2013, the following quadratic equation models the sales of new cars, where S, capital S of X, again, that's not S times X, that's function S, and it's a function of the variable X, represents the sales in millions. T equals 0. So T is like time. X is like time, except in this case, it's not in seconds, but in years. So 0 is 2000, right? So they start at 2000. 2000 is 0. So 2001 would be 1, and so on, right? So it's years after 2000. So X equals 1 represents 2001, and so on. So 13 would represent 2013. All right, it says use the model to estimate the sales in 2013. How does the estimate compare to the actual? So they told us what the actual is. This is a prediction model, but we know what the actual is, and we want to just compare the two. All right, so find out what our prediction model thinks about how many cars would be sold in the year 2013. So we'll call that S sub 13. Yes, it's the year 2013, but X for us is not the year, but the year since 2000. So we want 13 there. All right, and so that's equal to 0.0538 times 13 squared minus 0.807 times 13 plus 8.84. And so really you just pick up your calculator and plug that in. This is not something we would expect you to do without a calculator. So plug that in. So S sub 13, I get, we get 7.44, let's put that up here, 7.4412. All right, so that doesn't mean 7 cars were sold, right? Because it says sales in millions, so that's 7.44 million. So that would be 7, 441, 200. All right, and they told us that 7.6 million were actually sold. So that means our estimate is a little lower than what we expected, right? This is what the estimate says. And so ours was, 200,000 less, something like that, right? So we actually sold more than what the model predicted. All right, so part B, according to the model, in what year did sales reach 5.9 million? And then round down to the nearest year. So go ahead and do that, pause the video, and then figure out what you think that one is. All right, so this, we want to put this not as 5 million, but 5.9, because the function is in sales in millions, so we need to put 5.9 for the final amount that we want. We just don't know what time frame it is, right? What the time is or what the X is, but we know what the car sales is that year, okay? Or when we're going to hit it anyway. And again, this will be sort of an estimate, so we could do 0.0538 x squared minus 0.807 x, and then plus 8.84, and we just want to solve this. So well, let's see, let's take this over to the other side. So we get 0.0538 x squared minus 0.807 x plus, we move this to the other side, that gives us 2.94 equals 0. All right, so we need to solve this quadratic equation. So really, I mean, yeah, you could multiply through by, what, 10,000 to get all the decimals out, but I think probably just plugging all the A, the B, the C in to the formula, the quadratic formula, would probably work best here. So x is equal to 0.807 plus or minus the square root of 0.807, put that in parentheses, squared, minus 4 times 0.0538 times our C, 2.94, and then all of that is over 2 times 0.0538. All right, and so probably just, take all of that, put it in your calculator, figure out and take the square root of that. So what is that? So that's 0.807 plus or minus, and then on the bottom we have 0.1076. All right, so what does all that? The radicand, take the square root of all that. I get 0.136. And so now you want to just work through with the plus sign, get the value, work through with the minus sign, get that value. And so we're going to estimate. And so that means we're going to have something like 6.23 and 8.76. All right, so I mean, what we're going to do is just say, okay, because it's in the 8th year, right? So it's 8.79, almost the 9th year, but we don't want to go up. We want to say, when did it reach it? So it's kind of a wacky question, and like, okay, so how should I turn this into? We want to think of this as 6 going down, and this is 8. So in the 6th year and the 8th year is when we hit our max, reached our goal of 5.9. So 2 years. So we'd say 2006, and then we'd say 2008. Okay, because this is the 8th, well into the 8th year since 2000. So it's almost 2009, but not quite. It's still in the year 2008. So that's why we're sort of rounding down. We're truncating those rather than rounding. Okay. All right, so that's just an example of sort of modeling. They give us the equation already, and we just have to be able to use it both ways. Put an x value in, evaluate it, and then plug in, like if we know the answer, we plug that in and look for the x. So we kind of should be able to do that for any of these types of equations that we come up with. All right, and then the homework due next class is this down here. Remember that times 3 means the multiples of 3. So, that's 27, that's 30, that's 33, and that's 36. All right. And then A, of course, means all. And then I just have these listed individually. Okay. So do next class.